projectiles, type 2, landing below the plane. So in this case here we have a straight vertical cliff is 200 meters high, and a particle is projected from the top of the cliff, and we're given the speed of projection is 14 root 10 meters per second, and it's at an angle alpha to the horizontal. So if we were to draw this, we have our cliff, we have the ground below, and our cliff is 200 meters high. And the particle is projected at an angle. So therefore, it's projected up into the air at a speed of 14 root 10 meters per second at an angle of alpha to the horizontal. And of course, with this projectile, as it goes up, it's going to come down, but this time it's going to land below the plane. Unlike in the last case where on landing we were able to say that Sy was equal to 0, we cannot say that in this case here. Instead, what we say is on landing, Sy will be below where it started, and it's 200 meters below where it started. So if the initial velocity is in an upward direction, it will have gone up a distance and down the same distance, but then down the height of the cliff, which is 200 meters. So if it goes up x and then down 200 meters, essentially its displacement from start to finish is minus 200 meters. So again, that's going to be our key to solving here in this case. Okay, so again, we're given one other... No, we're not given... Oh, yeah, sorry, we're told the range from landing is also ground level at a distance of 200 meters from the foot of the cliff, whereas the straight vertical cliff is also 200 meters. So therefore our range, our S in the x direction, is 200 meters. Okay, so again, you're going to draw out your table if you haven't already done so. And you're going to mark in U, A, V, S and T in both the X and the Y direction. And in the previous example, I had reminded you of how to set up your initial velocity, so I'm not going to be doing that again in this question. So if you've forgotten how to resolve your vectors, go back to the previous video for type 1 of how to set up U in the I and the J direction. So we don't know what alpha is in this question, so therefore our U in the x direction will be U cos alpha, and our U is 14 root 10. Our U in our y direction is U sine alpha, so that's 14 root 10 sine alpha. Again, we're moving the horizontal plane, therefore there is no gravity in the x direction, gravity only acts down. And therefore, because we are projecting the object up into the air, its initial velocity is upwards, which is given the positive sense of the direction, and therefore g is in the opposite direction, therefore we assign a negative value for g. We remember that v is equal to u plus at, so therefore v in the x direction is 14 root 10 cos alpha, and v in the y direction is equal to 14 root 10 sine alpha minus gt. We know that s is equal to ut plus a half at squared, so therefore s in the x direction is 14 root 10 cos alpha t, and in the y direction we have 14 root 10 sine alpha t minus a half gt squared, and obviously time is with respect to t. Okay, so the first thing it wants us to do is to find in terms of alpha the time taken for the particle to hit the ground. So we know that the time for the particle to hit the ground is from start to end, and on landing we know that Sy is equal to minus 200 meters, and we also know that the range is equal to 200 meters. So we could use either of these pieces of information to work out our time of flight, but if I compare s of x with s of y, it is much easier to try and isolate t on its own with s of x. And we know the value of s of x is 200 metres on landing. So for part 1, we're saying on landing, s in the x direction is 200 metres. So therefore, if I take my equation for s of x, it's 14 root 10 cos alpha t. Then if I let that equal to 200 metres, then I can get t is equal to 200 divided by 14 root 10 cos alpha. And again, I could simplify that down if I wanted to, or just keep it as is. And the second part of the question is an interesting one because it wants us to show that the two possible directions of projection are at right angles to each other. So we know when two things are at right angles to each other, in other words, perpendicular to each other, then their slopes will multiply to give us -1. So we're going to use that fact that we know from maths to prove that these two are at right angles to each other. So therefore we need to find their slopes. So we also need to remember that slopes in maths can be found by getting tan theta. So therefore if I can get two slopes, in other words two tans, then I can multiply them and see do I get -1. Because obviously we're not going to have coordinates here to get rise over run or y2 minus y1 over x2 minus x1. So in applied maths, when we're looking for slopes, it's generally we're getting tan theta, which is our slope. So how are we going to do that? Well, we know that when landing, that sy is equal to -200 metres. So we've already used s of x is equal to 200 metres. So the next piece of information we have is that on landing, sy is equal to -200 metres. So we're going to take our equation for s of y, and s of y is 14 root 10 sine alpha t minus a half gt squared. And you can see I didn't simplify t for this reason, because t above is over 14 root 10, and here I have a 14 root 10. So it just makes it a little bit easier to simplify when I sub in for my time. But if you didn't spot that and you did simplify, don't worry, it's still going to simplify regardless. And then we have minus a half g times t squared. And then that must equal -200 metres. So if I look at how can I simplify, well, 14 root 10 is going to go into 14 root 10. I have sine alpha over cos alpha, which is going to give me tan alpha. So I have 200 times tan alpha. In the second bracket there, that should be t squared. So that's 200 over 14 root 10 to be squared. So if I simplify that, I have minus g over 2 times 200 squared, and 200 squared is going to be 40,000, and that's over 14 root 10 squared, and 14 root 10 squared is 1960, and that's over cos squared alpha, and then that equals -200. Now, if we spot that, you should remember that 1 over cos alpha is sec alpha, so 1 over cos squared alpha is equal to sec squared alpha, but of course sec squared alpha is also equal to 1 plus tan squared alpha. And again, all of those are in your maths tables, page 13, and again, commonly used identities in trig and maths, but also in applied maths for this section. So therefore, if I simplify out that bracket, what am I left with? Well, in applied maths, we love getting nice numbers. We don't tend to get awkward numbers that often in applied maths. So what you'll actually notice here is when I multiply out my brackets, g times 40,000 over 2 times 1,960 actually simplifies down lovely and neatly into 100. And then if I take out my 1 over cos squared alpha, that becomes sec squared alpha, which becomes 1 plus tan squared alpha equals minus 200. So multiplying out the brackets and rearranging, well, that gives me 200 tan alpha minus 100 minus 100 tan squared alpha plus 200 equals 0. So I'm going to get a quadratic here. And if I divide everything across by 100 there, that simplifies down to give me tan squared alpha minus 2 tan alpha minus 1 equals 0. Now if I look at that quadratic, there is no number that's going to multiply to give me minus 1 and add to give me minus 2, which means I have to go directly to my minus b formula. So if I move on to the next page there and we take that quadratic, what we have is tan squared alpha minus 2 tan alpha minus 1 equals 0. So a equals 1, b equals minus 2, and c equals minus 1. So therefore that's going to be tan alpha equals minus b plus or minus the square root of b squared minus 4ac all over 2a. So subbing into that equation our a, our b and our c, that gives me tan alpha is equal to minus minus 2, which is plus 2, plus or minus the square root of b squared minus 4 times a times c, and that's all over 2 times a. So subbing that into my calculator gives me 2 answers for tan alpha, and it simplifies down to give me 1 plus or minus the square root of 2. So as I said, we have to note that our slope is equal to tan alpha. And therefore we have 2 slopes. So we have tan alpha can equal 1 plus root 2, or tan alpha can equal 1 minus root 2. So in other words, we have m1 equals 1 plus root 2, or m2 equals 1 minus root 2. And therefore, if I check m1 times m2, well, that gives me 1 plus root 2 times 1 minus root 2. And therefore, 1 times m1, or m1 times m2 gives us 1 times 1, 1 times minus root 2, 1 times root 2, and root 2 by root 2 is minus 2. And of course, root 2 and minus root 2 is 0. And therefore, lo and behold, I'm left with 1 minus 2, which is minus 1. And therefore, we're using our theory from maths to say, therefore, our slopes are perpendicular. And if the slopes are perpendicular, that means then that the angles of projection are at right angles to each other, which is what they wanted us to show. Okay, so let's have a look at where were we getting our marks for. So if we go back to the start, we had to get our time first of all, which was 200 over 14 root 2. So that was 5 marks going for that. We then had to get our second part, which was by letting it equal to minus 200. So by letting this equal to minus 200, we were getting 5 marks. And subbing into the equation was another 5. And then literally all of the rest of your work was only going to be worth 5 marks. So a lot of times in applied maths, the bit that you're getting stuck on you're only going to be losing 5 marks. Most of your work is actually going for the setting up of the question. So it was only a 20-mark question for this. But a nice question all the same.